the one you need to know. I'm the map. I'm the map, I'm the map. If there's a place you gotta get, I can get you there, I bet. I'm the map. I'm the map, 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 I'm the map!
Hi everybody, welcome back to Orgoland, lecture 25b. Just wanted to let you know that there is one goal and one goal only for the rest of the semester. Here it comes. How many different functional groups can you make? How many can you be in control of changing? That will be our goal, and we talked about in the last lecture how you might be able to create an Orgoland map to help you figure out these roads to get to all these different functional groups. So I'll keep harping on that theme. Sorry. It's just a really cool theme for Orgoland since it is a place. All right, so today's class, let's look at what we're going to happen. Here are the sites from today. I hope you enjoy these pictures of where we used to be able to hang out. But now we're hanging out in this virtual Orgoland world. And so for today's class, we're going to look at sections 10.3, which we've already had assigned in a previous class, meaning way a long time ago, so it's going to be somewhat of a review, and section 10.4, which is also somewhat of a review. So there's a lot of review in today's lecture. Feel free to fast forward through any part that you think you already got. Okay? All right. Preparation of ethers. Very cool functional group. And I'll show you a few examples later on of where it's used in nature and such. But there are two ways to actually make an ether. So let's make sure we're clear about this so that we know how to get to ether meadow, as it says up here. Ether meadow. That's really cute. That might be right behind me. There it is right there, right before the tower. It is now officially called ether meadow. Okay, so here is the Williamson ether synthesis. That is the most familiar synthesis that you guys know of how to make an ether. Just so you know, here is Williamson, strapping young lad in the 1850s. But boy, he was he did a lot considering he was blind in one eye and couldn't use his left arm. Imagine that. And he still was came up with this very, very popular synthesis that he got his name after. Can you tell I'm jealous? I don't have a name reaction associated with me. Oh, someday. Okay, so here is his synthesis, but we've seen it before, we just never called it this. It's when we use the alkoxide ion as a nucleophile. So we have seen this alkoxide ion and you actually know how to make one. I'll show you that again. This is very familiar to us. This is a very strong base, right? Very strong base. And therefore, I can only do this reaction with a primary aliphatic carbon. Do you remember why? And what would happen if I use this strong base on something other than a primary? Not good. I would not get this beautiful ether, which is this molecule here. So ethers are any kind of single bonded O that's attached to two R groups. The R groups cannot be hydrogens. If they were, then it would be called an alcohol, when you know it. So this is what we're going to try to do. And we have seen how to make these alkoxides before.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercurium, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium. and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
So, this is the beautiful reaction of any alcohol. And what I want you to remember, and maybe remind you about, is that beaker was containing nothing but pure ethanol to start with. And so when this reaction is done, the sodium metal is most likely the limiting reagent in this flask. And so you will have a lot of this alkoxide. Oops, what happened to my pen? There it is. You're going to have a lot of this alkoxide, but it is going to be dissolved in a lot of ethanol that's left over. So it's a solution of sodium ethoxide in ethanol. But it's a lot of fun to play with if you want your ethoxide. And so that's what we will do. Okay. So imagine you were asked to prepare ethyl isopropyl ether. What is that, you say? That's this molecule. Okay, so ethers, you just name the two R groups and put an ether at the end. Pretty simple nomenclature. Now, notice I have two boxes. That means there's actually two ways to make this ether. I have to decide which end of the alkane chain do I want to be the alkoxide. So there's two possibilities. I could put the alkoxide attached to the ethyl group and have it attack this secondary bromide. Or I could put the oxygen and alkoxide on the secondary aliphatic carbon and put the bromide on the primary aliphatic carbon. So you always have two ways that you can do this ether synthesis. Please keep that in mind, because both of them may not be the right way, right? Think about which one would give you a better yield of this ether. Both of these are using very, very strong bases in O-. And remember what O- will do to a secondary leaving group, right? Strong base with that secondary alkyl halide gives mostly an E2 reaction, and you will not make the ether. You would make lots of alkene. But if you have that bromide attached to the primary carbon, then you'll get a really good yield in an SN2 reaction. Okay? So let's practice this and see. Take a second. Can you tell me which of these reactions would produce this funny formula here? What I want you to do is at any time when I draw down the line structure, please feel free to, in textbook form, please feel free to draw it out into line structure. So you can blow it up and actually see what these three CH3s in a parenthesis would be. That is 3 CH3s attached to a carbon, this one, which is attached to an oxygen, which is attached to a methyl. Okay? So see if you can make this methyl T-butyl ether. Which one would you take? I'll pause. Okay. So let's look at each one of these. Okay? If I use, this is one possibility again. I could use this O-. This is the methyl alkoxide or methoxide. And I could react it with this T-butyl bromide. Those are all the right number of carbons, all the right number of species, but the problem is this is a tertiary alkyl halide. And so it is going to go through an E2 process because that alkoxide is a very strong base. The HCl one with this alkane chain, I just threw that in there just to see if that could mess you up. Did it? Hopefully you saw it and go like, wait, there's no functional group on that starting material. There's no reaction that's ever going to happen with this one. Sorry, I was just being a little crazy. Okay, so let's take a look at the next one. The next one looks interesting. Yeah, maybe I could. Maybe I could protonate this OH with the H plus and make it a good leaving group. And then the methyl could get attacked by the T-butoxide. Does that sound, well, what? Yeah, I know, you're right. Yeah, did you see this? This is an acid. This is a strong base. These two will fall in love with each other. Boom! They're the first reaction that's going to take place, and this is the product from that reaction. You would just make more T-butyl alcohol. Not good. So hopefully this last one is it, and if it's not, then maybe it is none of the above. So I got a big, bulky, strong alkoxide, but here is my methyl with the leaving group. So this can react easily to create and kick off the Br- with no worries, no sweat, no E2 is going to take place here. So it is one of the above. Oops, sorry. It is one of the above. It is D, golden child. Okay? We like this one. How'd you do? All right. So ether synthesis is pretty straightforward. But what if you don't have a primary alkyl group hanging off your ether? What if it's a secondary or tertiary halide? All right. How do you make ethers with, say, 2 tertiary carbons joined in the ether? This is method 2. And it's not that surprising. Hopefully this will feel familiar. What if I just took a T-butyl, right, with a leaving group on it, and I can't put the alkoxide in here because then I'll get E2. So let's just step back and remember, oh, wait, this is a tertiary, and this is benzylic. It's a tertiary benzylic. This leaving group will just fall off in a nice SN1 fashion. Off it pops. With a carbocation, and now I don't need a strong O-. I need its conjugate acid. I need its weakest base, so to speak, its weakest nucleophile possible, and that is this ethanol. So this would make this final product here of an ethyl group with a benzyl carbon. Now granted, this isn't the only way to make this one, because again, this example does have a primary carbon. But I wanted to show it to you because it came from lab 7. We've seen this reaction before when we stuck silver nitrate in here. Okay? Oh. I should always turn off my phone. Okay. Just like in class. Dang it. All right. So if I have silver nitrate in this reaction, then it's like lab 7. And the purpose of silver nitrate was not to act as a nucleophile, but the ethanol that was in the solution was the solvent and the nucleophile. So basically, this whole reaction had one species as the solvent and the nucleophile, and we call those reactions solvolysis. So solvolysis takes place, and it's a really efficient way to do an SN1 reaction because that alkyl halide is surrounded by massive, massive amounts of ethanol. And so it's going to bump into the ethanol. What's the silver nitrate for, you ask again? Let's make sure we're clear about that. This falls apart into Ag+. And Ag+ is going to see these two fall apart because hydrochloric acid is a strong acid. So they disassociate. And then as soon as everybody falls apart into their ions, there's 2 ions that never fall apart very much. Very little. There is a mad love affair between Ag+ and halides. Any CO-, Br-, I-, they all fall madly in love. Never to split apart and go back. And so what this reaction does is by adding silver nitrate, it drives the reaction forward, okay? Makes it go forward so that all of this Cl- is taken out and put into here. So this reaction is constantly trying to make more Cl-. Yeah, that's another name, dude. Le Chatelier, and therefore no reverse reaction here. So this reaction of silver nitrate and ethanol is very popular in an SN1 condition. But it also makes a beautiful ether. Woohoo! Ether. Okay. Try this one. Oh, be observant. All right, I'll give you 5, 4, 3, 2, 1. Ready? Okay, after you've paused, let's try this one now. Again, poor nucleophiles, poor bases. This thing has to do a poor SN1 reaction. And so this bromide will fall off, create the carbocation. And now here's the be observant part. It's an allylic, secondary allylic carbon next to a double bond. So what happens? Notice if I get resonance. What kind of carbon is the carbocation on now? Better or worse? First and last name. Tertiary allylic. Woohoo! Yeah, we like tertiaries for carbocations. Allylic even better. So it's going to stay there, which means our ethanol is going to react at that position. And after it reacts, it loses the H+, not before. Because I can never have O- in this solution, because O- is a very strong base and would cause E2. So please wait until after you add the ethanol before you remove H+. Okay? Here's a really cool ether. It's kind of like a little river running through behind us when it floods a little bit. It's called epoxide river. It's just a really cool kind of ether that's very popular. As I mentioned, this one's very popular in nature and very popular in organic synthesis. It'll take us to a lot of different places. So we'll come back and play with these epoxides, which is what a cyclic ether can turn into. So intramolecular reactions where we get an ether that's in a ring, and the ring that is most stable in nature, we found to be 3, 5, and 6. 3, 5, and 6 membered rings are the most stable rings that we see in nature. So these are the most stable rings that we can make with an oxygen inside of them, a cyclic ether. To do this though, it has to do an intramolecular reaction to close the ring. And to do this, it'll do it very quickly and doesn't need much help. All it needs is to put the OH in a backside position because we're doing an SN2 reaction here. So in a backside position, all it has to do is have the OH trans to the actual leaving group so that it can attack from the backside. So notice this OH, this becomes O-. And I didn't even need that strong a base to deprotonate it, just a little one. Not even sodium metal, because just a little gets deprotonated and it immediately goes to form this intramolecular cyclic ether. It's just so fast that the equilibrium is driven pretty strong by the smallest amount of O- that you can start to generate. Because as soon as this is here, it will immediately collapse and kick off the Cl. The proximity is so close, intramolecular, beautiful, and it's going to do this faster than any acid-base reaction, so I don't have to worry about an E2 elimination. And so it's amazing. I love epoxides. They're amazing. You get this beautiful stereochemical epoxide, and you can play with this molecule. It essentially has 2 leaving groups on it, and I can't wait to tell you that in a future video. It's going to be really fun to play with epoxides. So going to epoxide river right here, figuring out how to play with these trans halohydrins and get them into epoxides will be really helpful for us. And pretty soon I'll show you how to make these trans halohydrins, meaning it doesn't have to be Cl, it could be any halogen. So this is going to be a very popular river that we're going to meet and go through on our way to other little towns and suburbs. This is the nature catch for you. Did you know that this structure right here is actually what gypsy moths emit to attract males during mating? Look, it's got an epoxide. So they're in nature all over the place if you look hard enough. Pretty cool. Let's try some more fun. More fun. How do you synthesize these ethers? If I gave you these to play with, see if you can pause the video right now and try to figure out how to make these ethers. Okay? Ready? Let's see. This is the answers that I came up with. I started with this alkyl bromide, the T-butyl bromide, and phenol. Now, I think these would make a much better addition in an ether synthesis instead of switching it around. Because notice if I have it in this situation, I have my bromide leaving group attached to the benzene ring. Have we ever seen a nucleophilic substitution on a benzene ring? Ah, never. Okay? So, no nucleophilic substitution on benzene. So this is not good. I have to come out this ether synthesis from the other side. Okay? Ooh, look at this second one. I have a tertiary and a second, and a primary. So there might be multiple ways you could do these. There's no one perfect way, but this is one way that I saw that might happen. I could start with this alcohol and this T-butyl group, and then since this is on a tertiary, I don't need to make the alkoxide. I don't need to make it strong. So this is a gentle way to do an SN1 reaction, and it generally will not produce the alkene E1 if I just don't heat it. So over time, this would produce a nice, beautiful, beautiful scenario. If you wanted to do the other way, though, oops, looks like I got my structures backward. Oh, I missed a carbon. Ah! Let's change this problem. What if the OH was here? Let's make it, let's have some fun. Let's get rid of the primary and put it on a secondary. Oh my God! If I had it on a secondary like it is here, next to a tertiary, okay? Then this could be secondary. See? Change it anytime you like. All right, sorry for that little typo. Here, these two would not be a good mix because now I have the alkoxide and the D-butoxide down here, very strong base, trying to react with a secondary. It would have been okay to react with that primary up there, but not a secondary. I think that was the message I was trying to get across. And it just slipped through my fingers there. One little carbon. Oh, okay. How about this cyclic ether, this epoxide? That guy's really cool. How do you make that? Well, I highly recommend that you start by drawing your actual halohydrin with the OH and the leaving group in the plane of the paper, okay? And then you can draw them anti to each other on opposite sides with the wedge and dotted lines in the appropriate places, okay? So here now I can do this and create this, and notice this backside attack pushes the dotted line methyl that's behind, pushes it down. And that's how it gets over here. Okay? But sometimes you will not get such a glorious little drawing that has the OH and the leaving group anti to each other and in the plane of the paper. I wish every molecule was drawn like that. But sometimes you might get a molecule drawn like this. This is where we have the carbon chain, generally is always written in the plane of the paper, and the substituents like the Br and the OH are written as wedge and dotted lines. So when you see these, the danger is, how could you and can you turn this molecule into this one? Can you rotate it? Can you see how you can visually rotate the Br all the way to the bottom and push the methyl to the back and the hydrogen out in front? This is very hard visualization skills. So what I also recommend you do is that you determine these chiral carbons are our friends now, because now you can determine R and S for both of them. And as long as you don't change the chirality, then you've drawn it correctly. That makes sense? Cool. All right. No easy segue. Jump right to esters. Esters are very similar to ethers, and we've seen acetates in this synthesis before. But why should we care about esters? What's so important that you should learn about the functional group of esters? I was so excited about ethers and their epoxides. What's so cool about esters is that they smell. Oh, they have all kinds of smells. So here is a slide that shows you that you can take certain alcohols, and we won't look at this specific chemistry just yet, but I want you to recognize that you can just take specific alcohols and specific carboxylic acids of different carbon length chains and put them together to create esters that have all these wonderful different smells. So the perfume industry, the food industry, this is a very popular place for organic synthesis because we're always trying to develop that perfect smell, that perfect ooh, do Wellesley smell perfume that you could sell for like $500 an ounce. It's a great business. So organic synthesis has also taken over the perfume industry. Very cool. How do we make these esters? Let's just start with the most simple one that you've already seen. You've already seen this from how to make our secondary alcohols when we use this acetate to create the intermediate on our way to a secondary alcohol. So this synthesis is familiar. But just keep in mind, you could take any carboxylate. Any carboxylate is what it's called, with a CO double bond O negative charge, and attack it to any primary or secondary, even tertiary sort of work, but they're just going to go SN1 and go slowly and make a mess. So generally we do this reaction preferably with primary and secondary alkyl halides, because they will then immediately go SN2 with this really good nucleophile as an acetate, or any carboxylate that you use is a good nucleophile. Try this one. See if you can play with this. Pause. 5, 4, 3, 2, 1. All right, let's see what you came up with. Did you get this answer? Notice there's stereochemistry involved here. So notice the acetate did a backside attack on this secondary benzylic carbon. And therefore, we get inversion of stereochemistry at that spot. Is that what you got? Cool. All right. One last thing you can notice, this is 3 molar potassium acetate in acetic acid. So it's very common, as you'll see on the next slide, that we stick all of our negatively charged oxygens in solvents of their conjugate acid. Just in case they ever get a little excited and want to act basic, they can go act basic on their solvent conjugate acid and just make more base. It's just a good rule to follow. So try this even more fun. Woohoo! Even more fun problem. See if you can tell me what starting material you would use to create the ether on the first reaction. And then notice this monster molecule. Oh my God. Can you spy what the product would be and draw that? Might take you some time, but I'll let you play with it. See what you come up with, okay? Pause. All right, you're back? Cool. Let's, how'd you do the first one? This is what I came up with. And hopefully I didn't lose a carbon or two like I did in the last one. All right, did I get all the carbons? And in the heat of battle, I should just count them all. So I have 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I have all my carbons. Yes. Okay. So, as you can see from this reaction, I am not using the alkoxide again. I am just using the alcohol on a secondary carbon and hoping this does a nice gentle SN1 over time and pushes off and the leaving group falls off and I get this reaction. Notice why I wouldn't want to put the bromide attached to the double bond and do the opposite. Notice why that's a bad reaction. Have we ever seen a bromide attached to a primary carbon? Yes. Vinylic and act nucleophilic? Vinylic, nucleophilic? Never. That's like the benzene ring. Never. So this is very, very bad. Do not do this ever. Okay. So luckily we can go at the ether the other way. Okay? How about this last one? Looks like I'm adding an acetate. Notice it's swimming in acetic acid. It's conjugate acid. Very cool. What's this huge structure? This huge structure with 4 rings fused at one side is a steroid. This is the generic structure for all steroids. And steroids are pretty popular. I'm sure you've heard about them from muscle builders like myself. Yeah, they take the steroid. This is one precursor to that steroid, this synthesis if somebody wants to make steroids. This steroid here, trenbolone acetate, is very, very common for muscle builders to take as a steroid to build their bulk. But you know where else steroids are being injected and put into? Our cows. They want our cows to grow big and fast and muscles so we get lots of meat. And so they stick tons of steroids. And in this picture you can see I got a list. And it's not just this one steroid, but there's several steroids that they inject our cattle with to make them nice and big and do it really quick. It's just a fact of life. We like our steak and we want it. We got to have it. All right. No commentary really. Pro or con. It's just what happens. Okay. I thought I'd just show that to you. All right. I hope you've enjoyed this Ether Meadow, Esther Park, Ether Meadow River, Epoxide River, excuse me. So we're going to keep traveling through Orgoland. I hope you enjoyed this one. I'll see you soon. Stay safe, stay well.